tune the PID controller using one of the method is Ziegler-Nichols method. So the Ziegler-Nichols method basically it will requires you to use a table to calculate certain parameters for the PID controller. There are many more methods, but most of the methods are embedded in MATLAB, okay, or in programming tools. But Ziegler-Nichols method is one of the method that you can use manual calculation. Okay, so before that, we will go through what is the PID controller. So let's say you have a system that you want to control. So let's say you want to control a movement of robotic hand, for example, to turn to a certain degree, or you want to control wheels for certain rotations. So how you want to give command to this system? So basically you use programming, or you use something you control through monitor or remote control, for example. But how you want to make sure that this controller is accurate, okay? How you want to measure, and how you want to make sure that the system is controlled according to what you want. So you have learned about open loop system and closed loop system. So open loop system basically has no sensor that measures the output and compare the output with input. So that's open loop system. Meanwhile, for closed loop system, you have an important element, which is the sensor that controls the output and compares it with input, and then try to make sure that the output is within the certain range required, again, you desire. So the most basic controller is on-off control, okay, like your switch, okay, to turn off lights or turn on lights, okay. And for example, in thermostat, you can either on off the thermostat, okay, either when the thermostat has reached certain temperature, you turn it off. When the thermostat is cool, then you turn it on, okay. So the most basic controller is on off control. But on off controller is not automatic, okay. So you have to always either turn it on or turn it off. So if you try to plot the response of the on-off controller, so let's say this the square wave here, meaning the controller is on, and then the bottom one here, meaning the controller is off. So you will see that the temperature is in the form of like a wave, okay. So if you turn it off, then the temperature will drop. You turn it on, then it will take some time to reach maximum. So it's not when you turn it on, then it's not directly increased to maximum. It will take some time to reach maximum. So this is the things that you don't want to happen, okay. You want to make sure that when you turn it on, then the temperature increase to maximum as fast as possible. Okay. Okay, so in your block diagram, you have the plant, okay. The plant is the things that you want to control. So you add controller before the plant so that the controller will control the output of the plant. Okay, so PID controller basically has three components. So in this controller, basically, there are three components inside the controller. So you have P controller, I controller, and D controller. So P meaning proportional controller. So I integral, and D derivative controller. So there is an equation here. So we will go through later what is this equation, how these equations are derived, okay. So the idea of PID controller is that there are three components: P meaning proportional, I integral, and D derivative controller. Okay, so PID controller can be represented by this equation. So there are three elements in the PID controller. So the first gain, Kp, is for proportional controller or proportional gain. And then Ki over S is the gain, Ki is the gain for integral controller. And lastly, Kd is the gain for the derivative controller. So there is another, I would say, transfer function that is specific for the PID controller. So in previous lectures, you only learn about GS, okay, transfer function for GS. But when you add controller, or especially PID, then you have to add this transfer function Kp plus Ki over S plus Kd times S. Okay, so this transfer function is fixed, okay, meaning that you only need to determine the values for Kp, Ki, and Kd. And the form is fixed like this: Kp plus Ki over S plus Kd times S. Okay, so this transformation is in frequency response. So if you want to find the transfer function in terms of time, then the form of the transfer function will be in this form here. So Kp times epsilon t plus Ki integral of epsilon t plus Kd times differentiation of E over T. Okay, this is the things that I said previously. So PID controller has three components: proportional, differential, and integral. Okay, so this is an example of an output response of a system. So if you look here, there are several parameters that you can try to control so that you can produce an optimal transient response. Okay, the first parameter is rise time here. So rise time basically the time for the time response to reach steady state. Then there is an overshoot here. So you want to reduce the overshoot, and the rise time you want to reduce the rise time as small as possible and overshoot as small as possible. And there is the third parameter known as the steady state error. So you want to reduce the steady state error as much as possible. So there are three things that you want to control in a control system. You want to reduce rise time, you want to reduce overshoot, and you want to reduce steady state error. So the ideal response is the black line here. Okay, this is the one that is ideal that you want. Okay, but if you try to improve the time response by maybe increasing the gain, you will get either overshoot, or if you try to reduce the overshoot, then you will get a very slow response here. Okay, that is it is very difficult to get the time response as in the black line here, because you can either get an overshoot or your response is very slow. So we use PID to get a performance of time response as much as possible close to this required black line here. Okay, so the ideal one is the black line, and the red one here is your performance. Okay, the performance of your transfer function. Okay, so we look at the first controller, which is the proportional controller. So proportional controller basically causes the system to change in the set point or increase the time, the rise time, reduce the rise time. But however, it will cause this overshoot and damping. Okay. So if you add derivative to proportional controller, it will cause more damping and overshoot, but it will reduce the steady state error. Okay. If you look here, the blue line here basically reaches the red line. I mean, compared to the green line here, the blue line is closer to the steady values, meaning that if you add derivative controller, then the steady state error is reduced. However, you will see rippling or damping, and overshoot. And if you add integral controller, then the system will have no damping or overshoot. So the effect of proportional controller, it will reduce the rise time, but it will never eliminate the steady state error. Okay, that's the first characteristic of proportional controller. And for integral controller, it will eliminate steady state error, but it may make the transient response worse. So these properties here are individual, okay? Meaning that if you put proportional controller only, or if you put integral controller only and derivative controller only, so you need to combine all this together to get optimal effect. So if you put derivative controller only, then the system will increase in stability, reduce in overshoot, and improve the transient response. So this is a summary of if you try to combine two or more controller. So if you put proportional controller only, then steady state error still there, but the rise time is reduced. If you put proportional and integral, then the error disappears, but the system becomes more oscillatory, okay? Meaning that more damping. And lastly, if you put all of them together, then you can get the design specification that you need. Okay, this table summarizes the effect of each controller. So if you put only proportional controller, KP, then it will decrease the rise time, but it will increase the overshoot. And there is still steady state error, even though it decreased. If you put KI only, the integral controller, there will be overshoot, but it will eliminate steady state error, and the rise time will decrease slightly. And if you put only derivative controller, then it will decrease the overshoot. Okay, the overshoot will decrease, but there is still only small changes in steady state error and rise time. Okay, let's look at an example how to apply PID controller for a simple mass spring damper system. Okay, so this is a mass spring damper system connected with a spring and mass and damper, and the force is applied forward. So you can derive the transfer function. So this is the transfer function obtained from this system. Okay, let's say you are given certain values, and this is the transfer function after you substitute the value for mass, damper, and spring constant. So the goal now is to obtain the values for Kp, Ki, and Kd to obtain a fast rise time, a minimum overshoot, and small steady state error for this system. Okay, so let's say you apply no controller. Okay, so this system has no controller. So the time response will be as shown here. So it will rise to steady state by taking about 2 seconds. So here the settling time is given around 1.5 second. And a steady state error, which is you want to get around 1.0, but the system only reached about 0.05. So meaning that the steady state error is 95%. So very large, okay? So you want to reduce the steady state error, meaning that you want to get as close to 0%, and to reduce the settling time. So you add proportional controller KP to the system. So the transfunction, the overall transfunction has changed to a new form, okay? Because you have KP. So let's say you give KP equals 300. Then the system, the transient response will change, okay? Compared to previous one, where you see that the steady state value is around 0.05, which is around here. But now the steady state value has increased closer to 1.0. However, there is an overshoot, okay, and some ripple, okay, oscillation before reaching steady state. So if you add proportional controller, then the rise time and steady state error will reduce. However, the overshoot will increase. Okay, and although the rise time is reduced, but the settling time only decreased by a small amount only. So settling time is the time taken to reach steady state. Okay. So this is another example when you vary the value of KP. So here the graph for KP equals 100, and this is KP equals 300. So you will see the effect when K equals 100, there is less ripple or oscillation and less overshoot. But the rise time is slightly longer compared to K equals 300. So the rise time is about 0.1 second. For K equals 100, the rise time is around 0.2. Oh, ni lagi cepat. Okay, apa-apa je lah. Okay, so you add D controller or derivative controller to the KP, okay, to the proportional. Okay, so the trans function will change slightly, okay. And then you try to use KP equals 300 and KD equals 10. Then try to plot the time response. So you will see here that the overshoot now has reduced and the settling time also reduced, okay, becomes faster. So if you use only P controller, the rise time is about 1.2 second. But now if you include D controller, then the settling time is about 0.5. However, if you use D controller, there is only small effect on rise time and steady state error. So D controller only reduce overshoot and settling time. So this is an example if you varies the value of KD and the value of KD. So if you use KD equals 10, there is a higher overshoot and some oscillation. If you use high value of KD, then the overshoot is reduced. Okay, now if you replace D controller with integral controller, so you use KI over S instead, and you put some values for KP and KI, then you will see that the time response has reduced time rise time and slightly increased overshoot. But you need to be aware that here the KP is 30. So just now KP is 300. So if you put Ki, you must reduce Kp so that the effect of overshoot is reduced by reducing the value of Kp. So here, if you vary the value of Ki, so if you increase Ki, then the overshoot will increase. So small Ki meaning small overshoot only. So now we include all of the three components of PID controller, Kp, Kd, and Ki. And we give some values, and we can see that there is no overshoot here, and rise time is faster compared to if you use PD and PI controller only. And the steady state error is very small, around around maybe less than 5%. Okay, meaning that the steady state has reached closer to 1.0. So this is a summary. If you the summary for all of the controller combination. So P, PD, PI, and PID. So for PID, you can get the best time response closer to your desired time response. Okay, so the important things about PID is this equation. Okay, so you must remember that for PID you must have Kp plus Ki over S representing the integral, and plus Kd times S. Okay, or sometimes you can define this in terms of different parameters. If you factor Kp here, then the equation becomes 1 plus 1 over Ti times S plus Td times S. Okay, but the most common one is the first equation here. Okay, so now is the important part of PID controller lecture, is how to tune the PID controller. Okay, so given a transfer function, a system, a block diagram here with a plant and PID controller given here. So there are two ways to design PID controller. So the first method is by using mathematical model. Okay, if you know the mathematical model for the plant, then you can design PID controller using maybe MATLAB. Okay, but most of the time the model for plant is very complicated. Okay, because you can't obtain the mathematical model, so you have to tune PID controller manually using experimental approach. Okay, in case for mathematical model for the plant is very complicated to obtain. So the method to tune PID controller is known as Ziegler-Nichols method, okay, or Ziegler-Nichols rules. So Ziegler and Nichols proposed rules for determining the values of the proportional gain Kp, the integral time Ti, and derivative time Td, based on transient response characteristic of a given plant. So this method basically gives specific rules for determining Kp, Ti, and Td. Okay, so we look at the rules. Okay, so there are two rules, but in our syllabus we only cover the first method only, Ziegler-Nichols first method of tuning rule. Okay, so Ziegler-Nichols first method of tuning rules only applicable for the time response of plant to a unit step input. Okay, unit step input only. So if you have a unit step input, then you use first method Ziegler-Nichols. So let's say if you have RAM input, so you cannot use Ziegler-Nichols first method. Okay, so it's only applicable for unit step input. Okay, so this method applies if the response or the time response of the plant exhibit S-shaped curve. Okay, so let's say if your plant has this curve here, CT here, in the form of S shape, then you can use first method. Okay. Okay, so let's say this is the S-shaped curve, the time response for the plant. Okay, so first you need to determine two parameters from the graph. Okay, from the curve. So the first parameter is L equals the delay time. So delay time is the time when this curve start to rise. Okay, start to increase. So here it's somewhere from 0 until around here, okay, before it start rising. And then the second constant or parameter is time constant t. So time constant t, what you need to do is you draw a tangent line to this curve, and then find the intersection here at x-axis or time axis, and the intersection at steady state value. And then you determine the time from the intersection at time axis with the time at the intersection of the steady state value. So you will get the time constant t. Okay, so two things you need to determine from the S-shaped curve. First is L, delay time, and second is time constant. After that, you need to determine which controller you want to use. So usually you use PID controller, okay? So PID controller, to get KP, basically you use 1.2 times T over L. This is the formula, okay? So if come out in final exam, then this table will be given to you. Then to find the TI or the time constant for integral controller, then you calculate 2 times L. And lastly, for the derivative constant, the time derivative constant, you use 0.5 times L. Okay, after you get all these three, then you can substitute this in the equation for PID controller. Okay, so you substitute KP, TI, and TD calculated from the value of T and L and substitute in this equation. Okay, so this is your quiz. So submission is today before 12 a.m. And this is past year question. So first thing you need to do is to determine the transfer function GS. So GS is determined from this differential equation, okay? So you use Laplace transform. So that's the first step. Second step is you use the Ziegler-Nichols method, okay? So you find the value of T and L from this S-shaped curve. And then after you find T and L, you use the table in this slide, okay? Find KP, TI, and TD, and substitute in this transfer function to get the transfer function for the controller. Okay, that's the second step. And then after that, you simplify the block diagram to get the overall transfer function for the system. Okay, that's the steps, okay, for answering this question. Okay, so that's all for today's lecture. If you have any question, you can ask me anytime. Okay. Okay. Assalamualaikum and goodbye.
Thank you, sir. Waalaikumsalam.